Hi there. I'm really sorry about being late. Yes, there was confusion about the daylight savings time.
Yeah. Okay. So good morning. I'm going to introduce you, and then after that, you can share the screen. Okay. And let's study today's webinar. Good afternoon, everyone. This is Jung Gi-ryu from the School of Energy and Chemical Engineering, and I'm very sorry for any inconvenience caused by some delay because we are living in a different part of the earth, so there's some confusion of the time zone. Please understand the situations. Let me briefly introduce the biography of the Professor David Tilley. He got his bachelor's degree in chemistry in University of Georgia in the United States, and he moved to the California to pursue his PhD degree in chemistry at UC Berkeley. And after getting the PhD degree, he moved to this East Coast, and to have post experience in the Princeton, and then he moved to the Switzerland under the supervision of the Professor Kratcher. He did postdoc and also worked as a group leader for about 6 years, and then he got a faculty position in the University of Zurich in 2015, and then he was promoted to the associate professor in 2020. And he is one of the, in my opinion, he is one of the leading researchers in the field of PEC, especially among the young generation of the PhD scholars. And he especially specialized in this copper-based oxide, photocathode, and various kind of the analytic method for the PEC devices. And he achieved he published very interesting papers in the EES and Advanced Energy Materials and ACS recently, and he also wrote some insightful reviews in the Chem Society Review and the Advanced Energy Material recently. So I believe that he can give us very inspiring talk, and please welcome Professor David Tilley. Now you can share your screen.
Okay, let's see. Okay.
Yeah.
Does it look fine?
Yeah, great.
Okay. Dear Professor Ryu, thank you very much for that very kind introduction. It's my pleasure to be here to tell you about some research that's going on in our group. Okay, so I'll just get started. So basically, I'll just, the overview of our group activities. Today, I'm going to talk about water splitting, but we're interested in catalysis in general. And so in particular, putting molecular catalysts on surfaces. And so that's one new approach that we are looking into, the supermolecular approach, which is shown here in the middle. We're also interested in doing interesting chemical reactions. So different organic oxidation reactions in this case. And so, but today I just want to focus on water splitting. We're going to talk about this material such as this. Here, so let me find the pointer. Okay. I don't know if you can see my pointer. I hope so. Oh no, it's here. Okay, here we go. Here's a pointer. Sorry about that. Okay. Good. So I thought there were probably a rather broad background here. So I thought I'd give a rather general introduction, a little bit more in detail than I normally do. So I just want to show this this graph here about the total energy supply that we've used over the last decades. And what you see here on the y-axis is units of exajoules of energy. So 10 to the 18th joules. And if we now want to calculate an average usage rate, we can just divide that by the number of seconds in 1 year, and we get a number of 19.2 terawatts in 2019. So a terawatt is 10 to the 12th watts. And, just to put in perspective, a typical power plant is on the order of a gigawatt, so 10 to the 9th, so about 3 orders of magnitude less. So what you can see is that clearly most of the energy comes from fossil fuels, coal, oil, natural gas. This little red sliver here at the top, this other, that's what we're interested in. That's this solar energy, wind energy, geothermal. And it actually has grown a lot over the last decade, from 1% to 2%. So there's progress going on there. And but the energy needs are growing. So back in 2001, we were using energy at a rate of about 13.5 terajoules per second. And now in 2012, about 18 terawatts. In 2050, it's predicted by these authors here at the bottom that we're going to need energy of about 27 terawatts. And I would point out this is a rather conservative number because they already assume that we're going to get about 14 terawatts for free, just because we get better at better energy efficiency, better insulation, for example. So 27 terawatts. So how do we get there? Well, I mean, if we just take what we're using today, 19 terawatts, even if we can continue with business as usual, we're going to need about 8 terawatts extra. And so how do we do that? Well, we can take these 1 gigawatt power plants. We could build 8,000 new gigawatt nuclear power plants, for example. If we were to do that, we would have to start today and build a new power plant every day from now until 2045. And it seems quite difficult to do. We have to worry about regulations and such, but this is also going to be a problem with solar, right? Even if we want to build gigawatt solar power plants, we need to build 8,000 of them. Okay, then that's just to meet this 8 terawatts here. But actually, we're targeting net zero. And so, okay, what if we wanted to get everything, with solar, for example? Then we have 27,000 new power plants to build until 2050. So that's roughly 3 power plants per day that need to be constructed. So, but, as you can see in the picture, we've already gotten started. So that's a good thing. And of course, it doesn't have to be a linear increase, let's say, with time. It's definitely going to be exponential. So there's hope, I think. I just want to put into perspective the different resources, because I'm sure maybe people in the audience are working on different aspects of renewable energy. So I'm going to represent that with the size of spheres. So this sphere here represents 19 terawatts. That's the average burn rate of energy of our planet in 2019. So if we look at river hydroelectric, so this is the kinetic energy in rivers all over the world. We can, get some of that. We don't want to put a dam on every river, right? But we can use some small part of that to help make this, to help generate our needs. Biomass, 7 terawatts. And so here, again, we don't want to use all biomass on the planet for fuel. We want to eat, and the animals want to eat. So, but again, some small part of that can help us make the transition. Geothermal, now we're into a much larger scale, so this could potentially meet it. In this case, we can't get all the heat from the earth, right? But there's a lot, but we can get stuff that's near the surface, and that can be very useful for heating our homes, let's say. Wind, again, a large resource. Might be hard to get all of it as well, but so we're talking always small percentages, let's say, but it can also contribute. And finally, we have solar, 85,000 terawatts. And I should mention that maybe you've seen different numbers. I'm just using the numbers from this paper here. I think within order of magnitude, they're correct. This is probably a little bit conservative number for solar. But what this means is that 85,000 terajoules per second of solar power are striking the Earth's surface. So it takes into account nighttime. It takes into account cloudy weather and bad weather. So it's a huge resource. And so with just capturing a very small amount of that, 0.06%, then we could get 50 terawatts, which is maybe what we're going to need by the end of this century. So the solar resource is huge, but it's actually it's dilute. And I want to illustrate here how big of a panel, let's say, we need to build. So primary energy use in the EU was 2.3 terawatts back in 2008. And then so I asked myself, okay, so what is the necessary active area of a 10% efficient device that would be required to meet this energy demand if we're going to use the solar insolation of southern Spain, which has the highest amount of sun. And so what you see there is a very large device. So it's stretching from Madrid to Sevilla. And if we just put that over Switzerland, so we would need a device that's on the order of twice the size of Switzerland. So very large. But the Earth, there's many places around the world where there's not a lot of people living, there's not a lot of plants living, and deserts, for example. And so what these black spheres represent here is if you were to build 8% efficient devices, of this size, then that would generate enough power to generate 18 terawatts. So The point is there's enough sun. Even in Switzerland, with this very little amount of energy, if you had 20% solar cells or solar conversion devices, you would only need to cover about 5% of Switzerland in order to meet Switzerland's energy demand. So there's really enough sun. We just have to get better at capturing it and and scaling out. But this sort of illustrates the challenge that, I mean, the materials that we use, we're going to have to be using, making very large arrays. You know, I think 1 gigawatt solar power plant is going to be on the order of, 15 kilometers by 12 kilometers or something like that is some reference I found. Okay, so what are we going to use? Are we going to use batteries or fuels? And I would say we're going to use both. So here's a very nice paper. I just want to show a few figures from this because I find it very instructive. So what the authors did here was that they use batteries for day-night cycles, and then they use hydrogen for long duration energy storage. And so they make the hydrogen by electrolysis. You generate, you have photovoltaics that generate electricity, and then you run electrolyzers and make hydrogen. You can store the hydrogen, and then when you need it, you can put the hydrogen into a fuel cell and get the power back. So they used weather data of the U.S. for 39 years, I believe, so this is just 1 year of data, 2018, I believe. And so what you see here is that we have a demand of energy, which is in black, and they wanted to see how much solar and how much wind do we need to install in order to meet this demand, and then in this case just to break even so that we have just enough energy. So what you see is that in the early spring, there's more power being generated than we need. And so all this extra power can go into storage, in this case, charging batteries, which is in this dark purple, and then making hydrogen. And then eventually in the summer, we can take this and we get this hydrogen back. And then, we use the power, we get the energy back from the hydrogen because we need it, because actually there's less sun and wind in summer. And I guess in the US, we need this in the summertime for air conditioning of all these hot cities in the desert, whereas in Europe, it'll be storing energy from the summer and probably heating in the winter. So, and then if you integrate over these curves, you can see how much power or how much energy is being stored in hydrogen. And then you're also seeing how much energy is being stored in the batteries. But it's not enough to look at just 1 year of data. We really need to have a larger perspective, because the sun is not going to be shining the exact same every year, and also the wind is not going to be blowing the same. So for instance, what this shows is that you would have to have an installed capacity such that, basically energy that is generated and stored in 1980 is going to be needed in 1984, right? So we need to have multi-year energy storage, even decades, I would say. And so really the only viable option, I believe, is fuels. Certainly batteries are useful for day-night cycles. And what I like about this is that, once you have it in the hydrogen, you can store the hydrogen, you can essentially store it indefinitely. It's like a fossil fuel in that sense. It just hangs around. Okay, so why do we focus on hydrogen as a solar fuel? So here we take inspiration from nature. So if you look at photosynthesis, what nature does is to take water, use water as an abundant source of protons and electrons, and uses light energy to drive those electrons uphill, and then to reduce and eventually to store the energy in CH and CC bonds in sugar. So it's storing the energy in chemical bonds, and we make oxygen as a byproduct. And so if we zoom in on this process, what we can see is that we have two photosystems in series. Photosystem 2, where we have the water oxidation. So essentially, we absorb light, an electron gets pumped up here, and the whole is then passed to the oxygen evolving complex, where it oxidizes water. So essentially, this photosystem here is just ripping electrons out of water, and it's making oxygen as a byproduct. So now the electrons have higher energy. You can extract a bit of work, let's say, as you lower the potential here, and eventually it's going to combine with a photo hole from this photosystem. And in that process, you can make ATP. And then again, this is now a little bit higher energy, and eventually this ends up in this NADP plus reduction till you make NADPH. And so these are the energetic products of the light reaction. So at this point, the solar energy has been stored in chemical bonds. So that's the hard part. So if we look at NADPH, it's this rather complex molecule. And here's the business end of that is this pyridinium unit here, where we can take 2 electrons from this electron transport chain and proton. We use energy from light, and we make this this hydride here, this pyridinium. This hydride. So this would be complicated. We could use that, but it's much easier just to replace that big complicated molecule on the left with just a proton, right? So in this case, we can have a proton from water and 2 electrons, and then we can make hydrogen. So this NADPH is essentially like this, is essentially like nature's form of hydrogen. So now, once nature has now stored the solar energy in chemical bonds, now thermodynamics are on your side, and you just have to do some chemistry, and for that you need catalysts, right, to accelerate the kinetics. So enzymes or protein catalysts that do this. So you have this renewable sources of reducing agents, this NADPH, you reduce CO2 to carbohydrates, and that's biomass, what we know. So we could do a similar thing with industrial reactions. There are industrial reactions for carbon fixation. So for example, if we took green hydrogen, we could react it with CO2 to generate valuable products. So in this case, this would be the reverse water gas shift reaction, where we make carbon monoxide. And then if we combine that with renewable hydrogen, then we can make these things that we are used to, like gasoline, diesel, jet fuel. And if the CO2 comes from the air, then this, when we take the CO2 from the air, react it with green hydrogen, then we make renewable diesel, renewable jet fuel, then we can use it and it goes back into the air, but it's overall carbon neutral. And so this would be a nice approach towards, basically stopping this stream of taking the reduced carbon sources underground and keep putting them into the air. So I should point out there's also very interesting biological approaches. So if you take green hydrogen and you can engineer bugs and feed this hydrogen to the bacteria, and then you can make all sorts of interesting CO2 reduction products. There's also the Haber-Bosch process, which is very important for us, for our food. It has sort of enabled the population explosion. We reduce nitrogen with hydrogen to make ammonia, and then we use this ammonia to make fertilizer, and then with this fertilizer we can grow more biomass, and then we have more to eat. So this is a very large scale reaction, and I think something like 1% of natural gas production goes into this, or something like that, on the order of that, of the world natural gas production. So but essentially the way it works now is we take natural gas, and which mainly has methane, and then we can react that with water, and we make CO2 and hydrogen, and then we use that hydrogen in the Haber-Bosch process. So this electrolytic hydrogen is only about 4%. And I think the first step will be to take this green hydrogen and replace the fossil hydrogen in the Haber-Bosch process. That'll be sort of the near-term goal. And then eventually, though, with our technology, if it's scalable enough, then we can target, actually making an impact in the energy market. Okay, so how are we going to make solar hydrogen? Well, there's a couple of different ways. We can use photovoltaics, make electrical energy, and then run electrolyzers. And that's what was envisioned in this paper, this long duration energy storage paper that I mentioned. So essentially, these are advanced or rather mature technologies, photovoltaics and electrolyzers. I believe up until now, the largest electrolyzer is on the order of 10 megawatts, but there are recent funding projects from the EU that have, I think now there's at least 300 megawatt electrolyzers that are scaled up. So again, these megawatt is 10 to the 6th, we need to be 10 to the 12th eventually. But this is nice. It's nice to see that people are interested in hydrogen, I find. And so, we have to start now. And I guess that, so we use the mature technologies that we have. what I'm going to talk about today is this photoelectrochemical approach, where in principle, what it's doing is it's combining the photovoltaic aspects of a material and the electrolytic properties of its surface. So essentially, we can take both of these things and put it into one device. And there's potentially some advantages to doing that. You save on balance of systems costs, for example. And it's suitable to further adaptation, which can be very cheap in the future. So yeah, but I'll give an outlook about that at the very end. Okay, so now I'm going to switch into the topic of photoelectrochemical water splitting. So this is a similar. Okay, so this is now the idealized version of what I'm going to talk about today. So ideally, we would have a material that can be, earth abundant materials, ideally, because it's going to have to be spread, or have to have huge areas, it should be cheap to make. We hopefully has low energy requirements to synthesize it. So we're going to make a semiconductor, which has got this valence band and a conduction band and a band gap. And this can now absorb light and generate electron hole pairs. And what this dotted line here represents is a photovoltage. This is essentially the driving force that these electrons and holes can have to do work, and in this case, so in a photovoltaic, at the surface here, we would have a wire, and we would just extract these electrons into a wire, and we would make electrical current. But in our system, we're just going to replace this at the front. We're going to replace the wire or the contact with a catalyst. And here, now the electrons can be used directly to do chemical reactions. So in this case, we're going to reduce protons to hydrogen at the surface. And the holes can then are now in equilibrium with the Fermi level over here, the electrons, the electrochemical potential of the anode over here. And we see that this is now more positive, or let's say lower in energy than the electrons in water. So now it's downhill in energy for the electrons to move into the anode. And so we're going to oxidize water to oxygen. And this difference here is effectively the thermodynamic difference between these two reactions is effectively the energy that can be stored by doing this reaction. So we focus on the photocathode, but in principle, people usually talk about using photoelectrochemical tandem cells. So instead of having this metal anode over here at the left, you can also replace it with a light absorber, for example. And this way, you can have two different band gaps, which absorbs different portions of the solar spectrum. And so although this adds complexity and cost, the improvement in the efficiency is pretty dramatic on going from one absorber to two absorbers. And so this is seen as a highly viable approach for doing overall water splitting at a high efficiency and relatively low cost. So, but I'm just going to focus on one of these materials today. And so just to show you how to interpret the data. So this is what we typically do. See, my internet connection is unstable. I hope it's going to work now. Okay. So we have some material like this on the left, and we've connected it to the back contact a wire, and we can control the potential versus a reference electrode. And this reference electrode, in this case, well, we can then convert that to this reversible hydrogen electrode. So on this scale, 0 volts is always this energetic position here, proton to hydrogen. That's 0 volts. So in the dark, we would expect the current to come here. And so the fact that we have currents at earlier potentials means that we are storing some of the light energy in the hydrogen molecule. And so this is we are doing a light chopping experiment here, rather slow chopping. And so here's the dark. So in the dark, we apply potential and we see no current. And then when we are shining the light, then that's what we see here as a photocurrent. So just to put this in perspective, so I guess it's widely believed that in order to have a chance of having hydrogen at low enough cost, then the efficiency of your system needs to be at least 10%. Many people would say much more than that, but 10% solar to hydrogen efficiency corresponds to 8 milliamps roughly roughly 8 milliamps per centimeter squared. So you can see that we get to those currents here, but it's at a, we're actually applying quite a bit of electricity in addition to that. So the name of the game in our research is we get a curve like this. We want to push, we basically want to slide that curve to the right. And, so that means we would have an earlier onset potential. And so, you're right. So I should mention that that's one thing that we look for here. If we extrapolate this back, we can sort of estimate the photovoltage of that this is giving. So it's around 0.9, maybe 1 volt. And then we look at the current density at 0, which is sort of, doesn't make sense to apply much more potential than that. And then we also consider, here in the intermediate region where we have power conversion. So for example, at 0.5, we would consider, we would look at the current density there, because this is going to be important for, the tandem cell here when we bring in this other piece. Okay, so that's the data. So I want to introduce now copper oxide as a material. So copper oxide is very attractive because copper is very abundant and it's very easy to oxidize it. And you can actually make a pretty decent semiconductor by doing that. So it's intrinsically p-type due to copper vacancies. You can deposit it easily by electrodeposition as well. So the band gap is reported in the range of 2 to 2.2 eV. And so actually the material, what we produce in the lab we get an optical absorption and charge conversion around the band gap of 2. And so what this means is, so with water splitting systems, the solar to hydrogen efficiency is directly related to the current, which is directly related to the light absorption. So we can essentially calculate the maximum solar to hydrogen efficiency of this material just with the light absorption. And with that number, you get to 18%, I believe, with this, if you were to get every photon more energetic than the band gap here. So just to give you an upper bound, so we could easily hit the 10%, let's say. Good. So even though it's an oxide, when we stick this in water and we shine light, it's not stable. And so we have to make complicated structures like this. So what we see here is that this is a cross-sectional scanning electron micrograph image, and it's this false color, but so it's here to help us. So the copper oxide in this case is grown by electrodeposition. So first of all, we take a piece of glass, and on this glass we have a conducting oxide called fluorine-doped tin oxide, and in addition to that, we put gold, which has a better band alignment, let's say, with the copper oxide. It's going to facilitate getting the charge out of the copper oxide. So the Cu2O is there for photon absorption. The gold is there to extract the holes. So we're going to shine light from the front. We're going to make electrons and holes. The holes are going to move around and eventually get to the back. And then the holes can then be extracted out the back contact to the anode, where we'll do water oxidation. Now, the electrons are going to be generated and be moving around. And if they're lucky, they will find an electric field here near the interface of this electron extraction layer. And then they will move here and then be injected into this layer. So this zinc oxide, this aluminum doped zinc oxide forms a p-n junction with a copper oxide. And that just helps you to get the charge. So we're always fighting against recombination. We're absorbing light, making electron hole pairs. They will just, if you do nothing, they will recombine, and then you have heat, and that's not very useful, or less useful for us. So, so what we want to do is to generate these electron hole pairs and then extract them and then make them do work, either in a circuit to make electricity or to do chemistry like we're doing here. So the zinc oxide is also not very stable in water. So we put this TiO2 as a passivation layer. And I should point out, we do this by deposition, by a method called atomic layer deposition. And so we can basically grow very thin layers, with atomic layer control of different materials. So in this case, we use about 20 nanometers of zinc oxide and about 100 nanometers of TiO2. And basically this minimizes the chance that we have a pinhole. So if you have a small dust particle on there, we basically want to protect the copper oxide from seeing any water. We don't want water to directly contact the Cu2O. So then we photoelectrodeposit this ruthenium oxide, and this is a catalyst, and this is going to enable us to make hydrogen. So when we shine light, apply a little bit of potential, we're going to get electrons moving from the copper oxide into the catalyst, and then finally reducing protons to hydrogen. Okay, so I'm going to tell you a couple of stories. First from Winze. So he was eventually he came as a visiting PhD student and then came back as a postdoc. So he was interested in adopting the methodology of Minami in Japan, who was looking at oxidized copper foils to make high quality copper oxide sheets. And so the way you do that is you take a copper foil and heat it up to, I think, 1,000 degrees, 1,050 degrees, something like that. And you control the partial pressure of oxygen. And then you cool it down under controlled oxygen partial pressure. And when you do that, then you can make a very thick sheet of an oxide with very large grains, very high quality material. And so now we need to then, so we have our light absorber, we need to put something that extracts the electrons, something that extracts the holes. So we start on this, in this case, by doing this atomic layer deposition, where we, instead of the zinc oxide, now we use gallium oxide, because this actually has gives you a much better voltage. Right, and then on top of that, we put the TiO2 as a corrosion protection layer. So after we do that, then we sputter gold onto the back, and this is again as a hole extraction contact. So now we've got contacts where on either side. So we just need to connect a piece of copper wire to the back, package it up, which is epoxy here. And so this is now similar to what we saw before in the cross-sectional SEM. We have our copper oxide with our gold, where we can extract the charge out of this copper wire. And then we've got gallium oxide in this case, TiO2, and finally the ruthenium oxide catalyst. So now we can put this whole thing, so this epoxy protects the copper from the sides. These overlayers, these conducting overlayers, protect the copper oxide from this side. So now we can just directly put this in water and shine light and do chemistry. So this is what it looks like for just a cross-sectional SEM from the side. So we start with a 50 micron thick foil, and then after oxidation, it grows about 50%. And so the thickness here is about 75 microns. And it's a single crystal over this entire range. And I'll get more into that in a second. And if we zoom in on the surface here, we can see that, when we deposit our ALD layers, that yeah, it's roughly on the order of 50 to 100 nanometers is what we usually deposit here. Okay, so basically it worked, but I'm going to skip the details there so I can talk about something else. But we found that there were problems in this system, and so we have very complicated systems here, right? So we have a light absorber, we've got different overlayers, and we want to know what's going on at each of these interfaces. And so what we did is to use impedance spectroscopy to try to tease apart, where are the different problems in our system. And so I should point out that this work, the more recent work was led by Woo-Sok Yang, who's now an assistant professor at SKKU, very talented postdoc when he was in my lab. And so what we found was that we looked at different materials, so copper oxide, also antimony selenide, also silicon as a model. And we could identify, we could do impedance spectroscopy and identify the correct process which is associated with our light absorber. And what we found in the case of cuprous oxide is that we've got a resistive layer here, which is which I'll talk about later. And so the thought was, okay, that's maybe not super surprising. You often have surface states. It's at the light absorber, so we need to address this surface state, which would then remove this resistance, which would then give us higher currents. And so at that point, Winze came back as a postdoc and continued this work and looked at etching treatments. And I believe this was with ammonia etching. And so this is what under a light microscope, this is what the material looks like after just the thermal oxidation. And so it looks relatively homogeneous, maybe slightly different shades of red under the microscope. But each of these domains here are actually a single crystal, and they're differently oriented, as I'll point out. But right, so okay, so here we have the ammonia etching, and after this, we get this very interesting effect where you get a very different optical image or optical effect from each of these different grains. Excuse me, and this has to do with the orientation. So we can use this a technique called electron backscatter diffraction. And what we can do with this is to identify the orientation of the crystal. So it's this cubic crystal, and so it can be oriented in any number of ways and within this sheet. And each of these domains is going to have the crystal oriented in a different way. And so, for instance, we have these, it's mainly low index crystal group oriented, where these numbers are low, 0 or 1. And we can see nicely that, for instance, D here, this we expect where we have this cube with like the edge poking down. And in fact, we see in our SEM that we have this triangular pit. So this sort of, and this effect gives rise to this different optical effect where you can then see it with your naked eye. Essentially, we can see with our naked eye then the orientation of the different crystals due to this differential etching. And so here with the E, so this is the 101. So so it's like the crystal has been rotated up like this, and then with the F, it's rotated up like that. So that's very nice and interesting. Okay, now I'll just briefly show you the performance. So when we just take these sheets after the etching, we saw a nice improvement. So here again, we're doing the JV curves versus RHE. I believe we're in pH. I think we're in pH 7 for these experiments. We usually do pH 0, pH 7 with our stuff. So we have an onset potential, maybe 0.9, 0.95. We have, this is a value that we're interested in, 0.5. So our current density is on the order of about around 5, but after etching, you can see that we get much higher current densities. And in fact, if we go all the way up to 60 minutes, then we have even above 7 milliamps per centimeter squared at a very early potential. So this is very promising for tandem scale applications, and we are excited about that. So I mentioned that, we can see with the naked eye these different domains. And so what Wednesday did was then to go in there and break apart these samples and to then make individual devices of just single crystals, with different orientation. And what we found is that the devices that were prepared with high index crystals perform better. And so this is the current density at 0 volts versus RHE and at 0.5 volts. I should point out that these are very small devices, so we may have errors in the actual in the area measurement here, or the actual amount of light getting in. But I think relatively, we're looking at the relative current densities here. And then if we also have maybe a small difference in the onset potential, and these are just statistical distributions. And finally, the fill factor, which is basically how steep of the onset we have, that looks roughly the same here. And so we thought, okay, well, why is that? And so what we think is the case is that it's often the case with cuprous oxide that you get some oxidation, and we have CuO here at the surface. And then when we come to deposit the gallium oxide layer, we use this ALD process, and the chemical that we inject into the machine is reducing, and that you can have a chemical reaction. And essentially that can reduce the CuO to copper metal. And copper metal here at this interface is a recombination center. And it turns out that, so if you limit the amount of CuO here at this interface, then you actually dramatically reduce the amount of copper metal that's here, and then you have better performance. And it turns out that the cuprous oxide here is it can thermodynamically react in the same way, but it turns to be more kinetically stable. And so we think that with the high index facets, then they either etch more efficiently, or they don't reoxidize as fast in that short time when we're going from the etching solution into our ALD reactor. So that's an interesting finding, which was not at all intuitive to me, at least, that there would be a dependence of the orientation on the performance of these films, since it's a highly symmetrical unit cell. Okay. Good. So now I want to switch gears and talk about another material that we're investigating called antimony selenide. It's got a band gap which is very similar to silicon. So silicon is a low-cost material, or not low cost. It's earth abundant. The silicon is of course very abundant, but it takes a lot of energy to produce high-quality silicon solar cells. So that's why we're interested also in other light absorbers, copper oxide and antimony selenide here. So this is a low-cost material. So, right, this just means it's a good light absorber. And we can see that in nature, it grows in these one-dimensional spines. And if we look at the crystal structure, we can sort of see why that is. It's characterized as a pseudo 1D material. So you essentially have these ribbons, which are going into the plane of the board, into the plane of the screen here, and they are held together with weak van der Waals interactions. So that's what you see here in panel C here. So, right, it's easy basically to get these going in one dimension. And so in water splitting, so this material is just 10 years old or so, but water splitting started back in 2017 with the group of Moon and also with Wusok. And later that year, we published our work with our thin films, which were not nanostructured, and then later as well, a group in China, Yambo Li and Professor Xu. And then since then, there's been many others who have gone into this. And I should point out that Professor Moon has done a lot of really nice work on that in the years since. So I'm going to talk about Rajiv's first work, where essentially our method is, we try to do a low cost. We take again gold because it makes a nice ohmic contact at the back. It's a good charge extraction. We electrodeposit antimony metal, and then we selenize it at a relatively low temperature to get antimony selenide. And so we characterize it, we get the orthorhombic phase, and what we see here is it's primarily HK1 oriented, which means these one-dimensional ribbons are oriented, perpendicular to the substrate or a little bit at an angle. And so that's good for charge transport because we have higher charge transport along the ribbons than across the ribbons. And if we control the conditions well, then we can get these conformal films and we don't grow nanostructures. So this rather flat films, relatively, grains that are reasonably sized up to 700 nanometers. And so we thought, okay, well, let's just see if we get lucky and maybe we don't need any sort of catalyst or anything. So we stuck it in 1 molar of sulfuric acid and shine light. And so again, we're doing the light chopping, but we don't see anything. So it's either dead or it might be dead, and we don't know if anything's wrong here because also there's no catalyst. So then we put a catalyst on the surface and we use this molybdenum sulfide. And when we do that, then we get this nice current here, this onset of a photocurrent, which is very exciting. It's also noteworthy that this does not massively corrode. If we were to do the same reaction with copper oxide, we would get a massive corrosion current, and then it would just be totally dead. So it seems to be somewhat robust. So this was good, but we have a very late onset potential. We'd like to push this farther to the right to get more voltage. And so we did that. To do that, we tried to fix the surface. We also tried to fix the catalyst by doing this sulfurization, again, a low temperature process. And then when we do that, we get this very nice onset potential and better currents. And in fact, we haven't changed the band gap. So this is our quantum efficiency spectrum. So we're getting a lot more charge out. So we're getting less recombination all the way out to the band edge. And this was nice that it was stable. So we have, this is before we put a catalyst on. We just are using very harsh conditions, 1 molar sulfuric acid, and shining one sun, and we're just doing CV. And so what we see here is these are very low currents, but what we see here is now the reduction of the oxide on the surface, and then eventually it goes down. And then after this, we put the catalyst on the surface by photoelectrodeposition, this molybdenum sulfide, and then the material performs just as well as before. So this is not sulfurized. So what this told us is that it seems to be resistant or robust towards photocorrosion. So I mean, to improve the efficiency of this material, we can put different layers and different treatments on the surface. But even if we have a pinhole, it's not going to kill us because it seems to be robust. So we think this could be a pretty practical material. And so the further up work on this was just recently published. And so we wondered what is the sulfur doing? And it turns out that the sulfur not only fixes the bulk here, we have some surface states, which might cause recombination here deep. And the sulfurization treatment fixes not only that, but it also affects the bulk. And this is kind of interesting. So it seems that the sulfur can really get in between these ribbons and fix any defects that might be there in the bulk. Okay. So in my last short story, just very briefly, I want to mention copper sulfide. So this would be a really dream material because it's just so abundant, and you see how it compares in terms of band gap and band positions to gallium arsenide, which is gallium arsenide is a dream material in terms of performance, but it's very expensive to fabricate. And so it would be great if we could make copper sulfide work. And so 10% efficient solar cells have been made in the past, but it was eventually abandoned due to stability issues also in the solid state. And we thought we could address these stability issues, and so we dared to jump into this field. So just very briefly, the challenge with this, or the main challenge, is phase purity. So it can tolerate a huge deficiency of copper, and we're aiming for this very narrow red band here where we can get really stoichiometric copper to sulfide. And another challenge is that it has a short minority carrier diffusion length, which means that, when we shine light, we're only going to collect the electrons here from this blue point, but we need a much thicker film to absorb all the light. And so we're going to try to address that with nanostructuring, although I won't have time to chat about that today. But so essentially what we did was we wanted to do the solution processing method. And so we can take, in this case, bulk copper sulfide powder, which we can purchase, and we can dissolve it in this ethylene diamine solution and this mercaptoethanol. And when we can get a completely solubilized species, so we make molecular species, we completely dissolve it into this ink, and then we can go into a glove box, which is protecting it from air, and we can do spin coating and annealing, and then we can essentially make thin films that look quite good. So very beautiful black films absorbing a lot of light. And it turns out, I don't have time to go on the details, but it turns out that we actually do get phase pure material with certain optimized conditions, and you can check those details here. So it's actually rather thin, so we're not absorbing a lot of light, and that's one drawback of this approach. But so with this very thin approach, or this thin film, we can put over layers such as cad sulfide. This is again PN junction, then a protection layer, and again this catalyst. And so these are just different concentrations of this ink solution, and we can see that, at least with this intermediate value, that we get quite nice fill factor, let's say, and also decent currents. Considering that we have such a very thin film, which is not absorbing a lot of light, this is a high current. Okay, so in the final few minutes of my talk, I just want to describe where I think this is going. So I've talked today about the electrode type of photoelectrochemistry, but there's also a powder type where you don't need to extract charge, let's say, into a thin layer of metal. You can essentially, instead of doing chemistry for one reaction, you can do chemistry for both reactions. And this has some advantages. For instance, it can be quite cheap if you can make this work. But it's pretty hard to study what's going on. So when you're doing these experiments, you measure gases essentially, and you shine light and hope that you get a hydrogen and oxygen, and you'll get that at a certain rate, and then you can try to infer what's going on or what may be going on inside the particle. And although there's new methods that are getting better at sort of seeing what's going on, it's much easier to study what's going on in a thin film material where you essentially have half of a photovoltaic sort of system and then just one catalytic interface. We have just standard photocurrent photovoltage, but also some advanced characterization techniques such as impedance, which is very powerful, transient techniques. And so we can develop new materials here on top, and we can feed that, learn about them with these advanced characterization techniques, feed this into the synthesis, and we can further advance. And then eventually we can take what we've learned and apply them to powder systems, which can either just powders in water or photocatalytic sheets. And these can potentially be much cheaper and even compete on a price basis with fossil fuels. Right, so in the future, I see this co-development of PEC and photocatalysis, and we're excited about that. We're starting some activities in this photocatalytic field. Okay, so that's the end of my time, and I'm just want to thank the people who did this work. So this is just the current group members. Of course, the work I talked today is, I tried to mention them as I went along, and my external collaborators, funding mainly from the university and the Swiss National Science Foundation. And I thank you for your attention. I don't hear anything now. Oh dear, am I online? I don't hear anything, sorry.
I'm sorry for the inconvenience. So we have some questions. So maybe you can check the chatting window. So there are two questions. So basically, it seems that copper oxide is better than antimony selenide. So have you tried copper oxide photocathode for tandem PC cell? If so, does the tandem PC cell affect the performance of this copper oxide photocathode? And what is the STA efficiency of the overall PC water splitting cell? You can check the chatting window.
Yeah, okay. Thank you for the question. Yes, we have made tandem cells with copper oxide. Our first, in one of the slides, I showed an image of copper oxide paired with bismuth vanadate. So together with Kevin Civula at EPFL, we made, and I think Roel Vanderkral, I believe, provided the bismuth vanadate. We prepared a tandem cell with that, and I think that was the first demonstration of a tandem cell between copper oxide and bismuth vanadate. So there, the efficiency, your efficiency is limited by the smallest band gap, and so in that case, the copper oxide is the smaller band gap, and it's 2 eV. In practice, we did not get the maximum current from that, so I believe, I can't remember, but I think it was less than 1% the solar to hydrogen efficiency. But since then, people have used these two materials to make more efficient solar cells, and I believe it's over 3%. I think 3% is now the maximum solar to hydrogen with copper oxide and bismuth vanadate. I mean, you said that copper oxide is better than antimony selenide. I mean, in a way, I mean, they both have advantages and disadvantages. So I mean, so copper oxide, it's the disadvantage is that it's not stable in water, and therefore you have to protect it. But there's ways you can get around that. So for instance, you could make especially with particles, or if you have, you can or isolate different parts of the copper oxide so that it's effectively pixelated, and so therefore if you get some corrosion event somewhere, that it doesn't destroy your whole film. So that's one strategy there. The antimony selenide, the main challenge is that it's the photovoltage is still pretty poor at this point, and so there has to be some more fundamental work there.
Okay, I also have some questions. So I found that you generally utilize the ruthenium oxide as a co-catalyst rather than PT or other catalysts. Are there any reason you utilize the ruthenium oxide?
Yes, so this I developed back when I was in the Gretzel group at EPFL, and so we saw that with platinum, so we would deposit ALD, atomic layer deposition TiO2, and then we photoelectrodeposit platinum, or sometimes also electrodeposition, or sorry, electron evaporation. Well, anyway, evaporation of platinum. But what we saw is that the performance, doing long-term stability measurements, the performance would degrade, and we attributed this to the platinum falling off the surface, and because then when we replatinized, then the current would come back. So we investigated ruthenium oxide as a catalyst that could potentially bind more stably to the oxide surface. And but it turns out, as you saw in the cross-sectional SEM, that actually we put quite a bit more catalyst there as well. So it's a bit of a confounding effect there, but we still use it just because it's much more stable. Okay. Eventually we will just have to, eventually we should replace it with something more earth abundant, but for our studies now, we just use it for stability.
Okay, if you have any question, you can click the raise hand icons, or you can type your question in the chatting window. So I have another question. So you also mentioned the characterization of the PC system. So as some researchers studying in the PC systems, I found that sometimes there is no standard PC cell actually, right?
Yeah.
So are there any opinion about the standard cells of the?
Yeah, I mean, that's interesting. I think I know that there's at Helmholtz Center Berlin, they are trying to build up, or I think they have built up a lab which is supposed to be more like a standardization facility, sort of like where, people will send their solar cells to NREL or whatever, or wherever to get measured, that you could basically send your material there and they would measure under standard conditions. So I think that's up and running. But in principle, yeah, I mean, we haven't used that, and yeah, we just have our home built cells, and everyone has their home built cells. But it's true that it's hard to, yeah, I guess I guess you always have to. I mean, the differences shouldn't be that much. I mean, I think your main loss, actually, when you have your photoelectrochemical cells, we have a quartz window where the light comes in, and we don't put any anti-reflection coating there typically, right? So we actually lose quite a bit of light from the reflection. So that's why we have lower current densities than we normally would have. But in the future, for an optimized cell, we would certainly optimize that. But yeah, so clearly it matters. But no, we haven't spent too much time on optimizing the cell.
Yeah. So are there any questions?
Okay, so I see another one in the chat. What are the drawbacks if we try managing the band gaps with multiple atoms? So maybe, I don't know, maybe you're drawing an analogy to SIGs or making oxynitrides or something. So, right, I guess, right. So if you take large band gap oxides and then you try to put in nitrogen or sulfur, then you can raise the valence band and have smaller band gaps and more light absorption. Yeah, I think it's an interesting approach, and I guess the challenge would be the synthesis of that material, and then if that's stable or not. But I guess it's shown that I mean, we can put overlayers on also in the there's mostly work with protective overlayers on photocathodes, but there's also a little bit of work out there on protective layers for photoanodes, and yeah, so I guess that's always something you could investigate for stability purposes.
Okay, I think we have the time limitation, so it's better to wrap up the webinar at this point. Let's thank the Professor Tilley again, and see you next time. Okay.
Thank you very much for the invitation.
Yeah. Bye.
Bye-bye.